Hello, my name is Yan Cui. I will talk about genomic data inequality and multi-ethnic machine learning. Genomic and other omics data are essential for precision medicine. However, over 80% of GWAS and clinical omics data were collected from individuals of European ancestry, which only comprise about 16% of the world's population. So there is a severe data disadvantage for the vast majority of the world's population. The figure on the left is from GWAS Diversity Monitor. Over 88% of all the GWAS participants are of European descent, and the diversity was not improved over past 10 years. From the figure on the left, we can see that the similar data inequality in some of the largest public clinical omics datasets. In many studies, here are some examples. People have observed ancestry-associated DNA mutations, epigenetic modifications, RNA and protein expression, and the reference intervals for clinical lab tests. The inadequate and incompatible biomedical data present a significant health risk for the populations of non-European descent. The data distribution differences among the ethnic groups also have important implications for machine learning with multi-ethnic data. Currently, the data foundation for building AI-powered precision medicine is imbalanced for the lack of adequate data for non-European populations. We use machine learning experiments to answer two questions. Will the data inequality lead to AI models with low performance for the data disadvantaged populations? And if so, how to improve AI model performance for these populations? For our machine learning experiments, we assembled tasks and the datasets using the data from the Cancer Genome Atlas, or TCGA. TCGA datasets integrates multi-omics data and clinical data with matched cancer outcomes of about 11,000 patients from multiple ethnic groups. The data inequality among ethnic groups exists across almost all cancer types in the TCGA datasets. So it provides an excellent test bed for the comparison of multi-ethnic machine learning schemes. The machine learning tasks for our experiments are to predict cancer outcomes from omics data. We want to distinguish between individuals with good and bad clinical outcomes. We used 4 clinical outcomes as a prediction target variables: overall survival, disease-specific survival, disease-free interval, and progression-free interval. Currently, the standard multi-ethnic machine learning scheme is to train a model using the mixture data for all ethnic groups, regardless of the cohort's ethnic composition. We call this learning scheme mixture learning. A not so frequently used alternative multi-ethnic machine learning scheme is to train a model for each ethnic group separately, using its own data. We call this learning scheme independent learning. We compared the mixture learning and the independent learning schemes using the machine learning tasks assembled from TCGA data. For example, this machine learning task is to predict if the glioma patient's overall survival time is longer than 3 years. The dataset contains protein expression data of 22 African American patients and 315 European American patients. The performance of the mixture learning model looks great. The area under ROC curve is 0.88. Unfortunately, almost all the machine learning works with the multi-ethnic data stopped here. However, if we further test the model performance on EA and AA patients separately, we can find that there is a large performance gap. While the model performance on the EA group is high, its performance on the AA group is much lower. So clearly, the overall high performance from the mixture learning model is driven by the high performance on the EA group. The mixture learning scheme may lead to unnoticed model performance disparity gaps if we do not test the model performance on each ethnic group individually. The performance of the independent learning model for the AA group is much lower compared with the performance of the independent learning model for the EA group. So both mixture and independent learning schemes may generate significant performance gaps between the two ethnic groups. We propose to use transfer learning to improve machine learning model performance for the data disadvantaged ethnic groups. In the transfer learning scheme, knowledge learned from the source domain, where training data is abundant, can be transferred to assist the learning tasks in the target domain, where training data is inadequate. In the glioma prognosis task, transfer learning improved machine learning model performance for the AA group. Transfer learning reduced the model performance disparity gap from the mixture learning by 42% and reduced the gap from independent learning by 68%. These are our deep learning and transfer learning models. The technical details of the models are described in this paper. These are the results of our machine learning experiments on some other cancer types, omics data types, and clinical outcomes. Here are more results on the comparison of the multi-ethnic machine learning schemes. There is a common pattern from these results, which is characterized by model performance gaps between the ethnic groups from mixture and independent learning schemes, and by transfer learning scheme improving the performance for the data disadvantaged ethnic group. We performed the machine learning experiments on 224 tasks to predict cancer outcomes using mRNA or protein expression data from EA and AA patients. A total of 21 types of cancers and 4 clinical outcome endpoints were represented in these learning tasks. The percentage of AA patients ranged from 6% to 25% in these learning tasks, with a median of 12%. The median percentage of mRNA or protein features that are differently expressed between the EA and AA groups in the 224 learning tasks was 10%, and 70% of the learning tasks had at least 5% differentially expressed mRNA or protein features. Among the 224 learning tasks, 142 had a performance gap larger than 0.05, and 88.7% of these performance gaps were reduced by transfer learning. The performance gaps from the mixture and the independent learning schemes are statistically significant, and the model performance improvement for the data disadvantaged AA group by transfer learning is also statistically significant. We want to discover the key factors underlying the ethnic disparities in machine learning model performance. We hypothesize that the data inequality and the data distribution discrepancy are the key factors underlying the model performance disparity between ethnic groups, and both factors can be addressed by transfer learning. To test this hypothesis, we performed the same machine learning experiments on synthetic data. The parameters of the synthetic data generator represent these two hypothetical key factors: data inequality and data distribution discrepancy between ethnic groups. Synthetic data 1 was generated using parameters estimated from the data for this learning task, which is to predict if the disease-free interval is longer than 5 years from mRNA data of 43 AA and 218 EA gynecological cancer patients. The synthetic data 1 simulates the data inequality and the data distribution discrepancy in the real data. For this synthetic data, the performance pattern is similar to that from the real data, which indicates the simulation model captures the key factors underlying the performance pattern. We use the simulation model to make synthetic data 2 to have data inequality but no distribution difference between the two ethnic groups. For this synthetic data, there is no performance gap from mixture learning. However, the performance gap from the independent learning remains. The synthetic data 3 has equal numbers of cases from the two ethnic groups, which means there is no data inequality, but it has a distribution difference between the two ethnic groups. Synthetic data 4 has no data inequality and no distribution difference between the two ethnic groups. For these two synthetic data sets, there is no significant performance gap from either mixture learning or independent learning. For all the synthetic datasets, transfer learning achieved best performance for the minority group. The machine learning experiments on synthetic data confirm that the performance gap from mixture learning is caused by both data inequality and the data distribution discrepancy between ethnic groups, while the performance gap from independent learning is caused by inadequate data for the minority ethnic group, and the transfer learning can reduce these performance gaps. In summary, biomedical data disadvantage is a health risk factor for the vast majority of the world's population. AI greatly empowers precision medicine, but in the meantime opens up a major pathway for this risk factor to assert its effects. Precision medicine will be less precise for the data disadvantaged populations, which will produce a new type of health disparities. The new health disparities can impact any disease where data inequality exists. Their negative impacts would be broad and will not be limited to the disease types or subtypes for which ethnic disparities have already been reported. Using transfer learning can reduce the negative impacts of data inequality, thereby mitigating the health disparity arising from data inequality. Yang is a postdoc working with me. He actually did this work, and I want to thank the University of Tennessee Center for Integrative and Translational Genomics for funding. Thank you.